Now comes the operational concepts. So conducting good research requires first retraining your brain to think like a researcher. So this requires visualizing the abstract from actual observations, mentally connecting the dots to identify hidden concepts and patterns, and since synthesizing those patterns into generalizable laws and theories that apply to other contexts beyond the domain of the initial observations. Researcher involves constantly moving back and forth from an empirical plane where observations are conducted to a theoretical plane where these observations are abstracted into generalizable laws and theories. This is a skill that makes many years to develop. It's not something that is taught in graduate or doctoral programs or acquired in industry training, and is by far the biggest deficit amongst PhD students. Some of the mental abstractions needed to think like a researcher include in unit of analysis, constructs, hypothesis, operationalization, theories, models, inductions, deduction, and so forth, which we'll examine in this concepts. The first concept here is unit of analysis. So one of the first decision in any social science research is the unit of analysis of a scientific study. The unit of analysis refers to the person, collective, or object that is the target of the investigation. Typical unit of analysis includes individuals, groups, organization, countries, technologies, objects, and many more. For instance, if we are interested in studying people's shopping behavior, their learning outcomes, and their attitudes to new technologies, then the unit of analysis is the individual. If we want to study characteristics of street gangs or teamwork in organization, then the unit of analysis is the group. If the goal of research is to understand how firms can improve profitability and make good executive decisions, then what will be the unit of analysis? It will be the firm. So in this case, even though decisions are made by individuals in these firms, these individuals are presumed to represent their firm's decision rather than their personal decisions. If research is directed at understanding differences in national cultures, then unit of analysis becomes a country. Even inanimate objects can serve as unit of analysis. For instance, if a researcher is interested in understanding how make web pages more attractive to its users, then the unit of analysis is the web page and not the users. So if we wish to study how knowledge transfer occurs between two forms, then our unit of analysis becomes the combination of forms, that is sending and receiving the knowledge. So understanding the unit of analysis can sometimes be fairly complex. If we wish to study why certain neighborhoods have high crime rates, then our unit of analysis becomes the neighborhood and not crimes or criminals committing such crimes. This is because the object of our inquiry is the neighborhood and not criminals. However, we wish to compare different types of crimes in different neighborhoods, such as robbery, assault, homicide, and so forth. So our unit of analysis becomes the crime. If we wish to study why criminals engage in illegal activities, then the unit of analysis becomes the individual, that is the criminal. Like if we want to study why some innovations are more successful than others, then our unit of analysis is an innovation. However, if we wish to study how some organizations innovate more consistently than others, then The unit of analysis here becomes the organization. Hence, two related research questions within the same research study may have two entirely different unit of analysis. Understanding unit of analysis is very important because it shapes what type of data you should collect for your study and who you collect it from. If your analysis is web page, you should be collecting data about a web page from actual web pages and not serving people about how they use web pages. If your unit of analysis is the organization, then you should be measuring organizational level variables such as organizational size, revenues, hierarchy, capacity, etc. This data may come from a variety of sources such as financial record, survey, who are presumed to be representing the organization, the CEOs, officers, rather than themselves. Some variables such as CEO pay may seem like individual level variable, but in fact, it can also be organizational level variable because each organization has only one CEO pay at any time. Sometimes it is possible to collect data from a lower level of analysis and aggregate that data to higher level of analysis. For instance, in order to study teamwork in organizations, you can survey individual team members in different organizational teams and average their individual scores to create a composite team level score. For team level variables like cohesion and conflict, we will examine the notion of variables in a greater depth in the coming sections. Next is concept, constructs, and variable. So, research can be exploratory, descriptive, and explanatory. Most scientific research tend to be of the explanatory type in that they research for potential explanations. Explanations require development of concepts and generalizable properties or characteristics associated with objects, events, or people, while objects such as a person, a firm, or a car are not a concept. Their specific characteristics or behavior, such as person attitude towards immigrants, firm capacity for innovation, and car's weight can be viewed as concepts. Knowingly or unknowingly, we use different kinds of concepts in our everyday conversations. Some of these concepts have been developed over time through our shared language, or sometimes we borrow concepts from other disciplines or languages to explain a phenomenon of interest. For instance, the idea of gravitation borrowed from physics can be used in business to describe why people tend to gravitate to their preferred shopping destinations. Likewise, the concept of distance can be used to explain the degree of social separation between two otherwise collated individuals. Sometimes we create our own concepts to describe a unique characteristics not described in prior research. For instance, technostress is a new concept referring to mental stress one may face when asked to learn a new technology. Concepts may also have progressive level of abstraction. Some concepts such as person's weight are precise and objective, while other concepts such as person's personality may be more abstract and difficult to visualize. A construct is an abstract concept that is specifically chosen or created to explain a given phenomenon. So a construct may be a simple concept such as person's weight or a combination of a set of related concepts such as person's communication skill, which may consist of several underlying concepts such as the person's vocabulary, syntax, and spelling. The former instance, weight, is a unidimensional construct, while the latter communication skill is a multidimensional construct. That is, it consists of multiple underlying concepts. The distinction between constructs and concepts are clearer in multidimensional constructs, where the higher order abstraction is called as a construct and the lower order abstraction are called concepts. However, this distinction tends to blur in case of unidimensional constructs. Construct used for scientific research must have precise and clear definitions that others can use to understand exactly what it means and what it does not mean. So, for instance, a seemingly simple construct such as income may refer to monthly or annual income, before tax or after tax income, and personal or family income, and is therefore neither precise nor clear. So there are two types of definitions: dictionary definitions and operational definitions. In the more familiar dictionary definition, a construct is often defined in terms of a synonym. For instance, attitude may be defined as a disposition, a feeling, or an effect. An effect, in turn, is defined as an attitude. Such definitions of a circular nature are not particularly used in scientific research for elaborating the meaning and content of that construct. Scientific research requires operational definition that define construct in terms of how they will be empirically measured. For instance, the operational definition of a construct such as temperature must specify whether we plan to measure temperature in Celsius, Fahrenheit, Kelvin scale, or many more. A construct such as income should be defined in terms of whether we're interested in monthly, annually, before or after tax, personal or family. Or one can imagine that constructs such as learning, personality, and intelligence can be quite hard to define operationally. Theoretically plan with construct A and a proposition that leads to construct B, then the empirical plane with the independent variable leading to hypothesis and dependent variable. You can see the figure 2.1, which is known as the theoretical and empirical planes of research. The term frequently associated with and the sometimes used interchangeably with a construct is a variable. Etymologically speaking, a variable is a quantity that can vary, example, from low to high, negative to positive, etc. So in contrast to constants that do not vary, that remain constant. However, in scientific research, a variable is a measurable representation of an abstract construct. As abstract entities, construct are not directly measurable, and hence we look for proxy measure called variables. For instance, a person's intelligence is often measured as his or her IQ, intelligence quotient score, which is an index generated from an analytical and pattern matching tests administered to people. So in this case, intelligence is a construct and IQ score is a variable that measures the intelligence construct. So whether IQ score truly measures one's intelligence is anyone's guess, though may believe that they do. And depending on whether how well it measures intelligence, the IQ score may be a good or a poor measure of the intelligence construct, as shown in the figure 2.1. Scientific research proceeds along two planes, a theoretical plane and an empirical plane. Those constructs are conceptualized at the theoretical, that is abstract plane, while variables are operationalized and measured at the empirical observational plane. Thinking like a researcher implies the ability to move back and forth between these two planes. So depending on the intended use, variable may be classified as independent, dependent, moderating, mediating, or control variable. Variables that explain other variables are called independent variables. Those that are explained by other variables are called dependent variable. Those that are explained by independent variables while also explaining dependent variables are mediating variables or intermediate variables. And those that influence the relationship between independent and dependent are called as moderating. Example, if we state the higher intelligence cause improved learning among students, then intelligence is an independent variable and learning is dependent variable. There may be other variables that are not pertinent to explaining a given dependent variable, but may have some impact on the dependent variable. These variables must be controlled for in scientific study and are therefore called control variables. So intelligence here become independent, then effort moderating, lead to academic achievement, mediating variable, and then earning potential, which becomes dependent variable. Check out the 2.2 figure, a nomology network of constructs. So to understand the differences between these different variable type, consider this example. So if we believe that intelligence influence or explains students' academic achievements, then a measure of intelligence such as IQ score is an IV, which is independent variable, while a measure of academic success such as grade point average is DV, dependent variable. So if we believe that effect of intelligence and academic achievement also depends on the efforts invested by the students in the learning process, that is between two equally intelligent students, the student who put in more effort achieves higher academic achievement than one who put in less effort. Then effort become here a moderating variable. Incidentally, one may also view effort as IV and intelligence as moderating variable. So if academic achievement is viewed as an intermediate step to a higher earning potential, then earning potential become DV for IV academic achievement, and academic achievement become mediating variable in the relationship between intelligence and earning potential. Hence, variables are defined as an independent, dependent, moderating, mediating based on the nature of association with each other. The overall network relationship between a set of related constructs is called nomological network. Check out in the figure 2.2. So thinking like a researcher requires not only being able to abstract constructs from observation, but also being able to mentally visualize nomological network linking these abstract constructs. Next is propositions and hypotheses. For this, refer to the figure 2.3 that shows how theoretical constructs such as intelligence, effort, academic achievements, and earning potentials are related to each other in a nomological network. Each of these relationships is called a proposition. In seeking explanations to a given phenomenon or behavior, each of these relationships is called proposition. In seeking explanation to a given phenomenon or behavior, it is not adequate just to identify key concepts and constructs underlying the target phenomenon or behavior. We must also identify and state patterns of relationships between these constructs, such as patterns of relationships, are called propositions. A proposition is a tentative and conjectural relationship between constructs that is stated in a declarative form. An example of a proposition is an increase in student intelligence causes an increase in their academic achievement. This declarative statement does not have to be true, but must be empirically testable using data. So then we can judge whether it is true or false. Propositions are generally derived based on logic or empirical observations. Because propositions are association between abstract constructs, they cannot be tested directly. Instead, they are tested indirectly by examining the relationship between corresponding measures of those constructs. The empirical formulation of proposition stated as relationships between variables is called hypothesis. See the figure 2.1 for this. Since IQ scores and grade point average are operational measures of intelligence and academic achievement, respectively, the above propositions can be specified in form the hypothesis and increases in students' IQ score cause an increase in their grade point average. Propositions are specified in the theoretical plane, while hypotheses are specified in the empirical plane. Hence, hypotheses are empirically testable using observed data and may be rejected if not supported by empirical observation. Of course, the goal of hypothesis testing is to infer whether the corresponding proposition is valid. Hypotheses can be strong or weak. Students' IQ scores are related to their academic achievement is an example of weak hypothesis since it indicates neither the directionality of the hypothesis, that is, whether the relationship is positive or negative, nor its causality, whether intelligence causes academic achievement or academic achievements cause intelligence. A strong hypothesis is students' IQ scores are positively related to their academic achievements. A still better hypothesis is students' IQ scores have positive effects on their academic achievements, which specifies both the directionality and the causality. That is, intelligence causes academic achievement and not the reverse. Also note, the scientific hypothesis should clearly specify independent and dependent variable. In the hypothesis, students' IQ scores have positive effect on their academic achievement. It is clear that intelligence is the IV, the cause, and the academic achievement is the DV, the effect. Okay. Further, it is also clear that hypotheses can be evaluated as either true if higher intelligence lead to higher academic achievements, or false if higher intelligence has no effect or leads to lower academic achievement. Later on to this, we will examine how to empirically test such cause and effect relationship. The statements such as students are generally intelligent or all students can achieve academics are not scientific hypotheses because they do not specify I and DV variable, independent and dependent variable, nor do they specify a directional relationship that can be evaluated as true or false. So the last operational concept is theories and models. A theory is a set of systematically interrelated constructs and propositions intended to explain and predict a phenomenon or behavior of interest with certain boundary conditions and assumptions. Essentially, a theory is a systematic collection of related theoretical propositions, while propositions generally connect two or three constructs. Theory represents a system of multiple constructs and propositions. Hence, theories here can be substantially more complex and abstract and of a larger scope than propositions or hypotheses. I must note here that people not familiar with scientific research often view a theory as a speculation or the opposite of fact. For instance, people often say that teachers need to be less theoretical and more practical or factual in their theory and more practical or factual in their classroom teaching. However, practice or fact are not opposite of theory, but in a scientific sense, our essential components need to test the validity of theory. A good scientific theory should also have practical value, while a poorly defined theory tends to be lacking in these dimensions. Famous organizational researcher Kurt Lewin once said, theory without practice is sterile. Practice without theory is blind, and both theory and fact or practice are essential for scientific research. So theories provided explanation of social or natural phenomena. So as emphasized, these explanations may be good or poor. There may be good or poor theories that describe some criteria that can be used to evaluate how a good theory is. Nevertheless, it is important for researcher to understand that theory is not truth. There is nothing sacrosanct about any theory, and theories should not be accepted just because they are proposed by someone. In the course of scientific progress, poor theories are eventually replaced by better theories with higher explanatory power. The essential challenge for researchers is to build better and more comprehensive theories that can explain a target phenomenon better than prior theories. A term often used in conjunction with theory is a model. A model is a representation of all or part of system that is constructed to study that system. Example, how system works or what triggers the system. While a theory tries to explain a phenomenon, a model tries to represent a phenomenon. Models are often used by decision makers to make important decisions based on given set of inputs. For instance, marketing managers may use models to decide how much money to spend on advertising for different product lines based on parameters such as prior year's advertising expenses, sales, market growth, and competing products. Likewise, weather forecasts can use models to predict further weather patterns based on parameters such as wind speed, wind direction, temperature, and humidity. While these models are useful, they are not necessarily explain advertising expenditure or weather forecast. Models may be of different kinds, such as mathematical models, network models, and path models. Model can also be descriptive, predictive, or normative. So descriptive models basically are frequently used for representing complex systems, for visualizing variables and relationship in subsystems. An advertising expenditure model may be descriptive model. Predictive model is basically a regression model that allows forecast of future events, where the forecasting models fall under this kind of predictive model. Normative models are used to guide our activities along commonly accepted norms and practices. Model may also be static if it represents the state of system at one point of time, or dynamic if it represents a system's evolution over time. So the process of theory or model development may involve inductive and deductive reasoning. That deduction is a process of drawing conclusion about a phenomenon or behavior based on theoretical or logical reasons as an initial set of premises. As an example, if a certain bank enforces a strict code of ethics for its employees and Jamie is an employee at the bank, then Jamie can be trusted to follow ethical practices. That's the conclusion. In a deduction, the conclusion must be true for the initial premise where, what is the initial premise? Certain bank enforces a strict code of ethics and reasons are correct. So in contrast, induction is the process of drawing conclusion based on facts and observed evidence. For instance, if a firm spent a lot of money on a promotional campaign, that could be observation one is considered, but the sales did not increase as the observation two, and the possible promotion campaign was poorly executed, that's a conclusion. However, there may be rival explanation for poor sales, such as economic recession or the emergence of a competing product or brand, or perhaps a supply chain problem. So inductive conclusions are therefore only a hypothesis and may be disproven. Deductive conclusions generally tend to be stronger than inductive conclusions, but A deductive conclusion based on an incorrect premise and also correct. So in figure 2.3, inductive and deductive reasoning go hand in hand in theory and model building. So induction occurs when we observe a fact and ask why this is happening. So answering this question, we basically advances one more tentative explanation as his hypothesis. We then use deduction to narrow down the tentative explanations of those most plausible explanation based on logic and reasonable premises, based on our understanding of the phenomenon under study. Now the researchers must be able to move back and forth between inductive and deductive reasoning if they are to post extensions or modifications if they are to basically understand the given model of theory or build better ones, which are the essence of the scientific research. Here we end this topic. We have a lot more to do and cover under social research. We will be continuing the next part of it. Before we say thank you, in conclusion, what we studied here is embracing operational concept empowers researchers to navigate the complexities of the studies with clarity and precision. So whatever we studied in the operational and we understood, there should be a clear thinking of the researcher. This shift in thinking lays the foundation for robust research methodology, accurate data collection, and meaningful conclusion that contribute to the understanding of the world. So this precision enables basically you to formulate hypotheses, design experiment, and analyze data more effectively. The operational concepts involve breaking down abstract ideas into concrete measurable variables. Here I end. Thank you so much.